not very good at this, but maybe with a little practice, I could tell myself to relax it. Will be better next time I try. And even if I still can't do it, you know that I'm gonna stick to it. Yes! It's all about going through it, and I'm gonna tell you why.
Whoopsie! Whoopsies, I made a mistake and it's okay!
It's okay! Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay.
It's okay!
Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsies, 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 whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay!
It's okay! Whoopsies are what it takes to get better and better every day. Whoopsies, 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 whoopsies.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today.
Whoopsie. Wait, was it yeah or woo?
I think it was woo.
Okay, say woo with us.
Woo! Better.
All right. Hello, guys. So, first off, let me introduce myself. I am Taylor. I'm the lead technical champion with Rootkit, and I am here in Elijah's stead today. We'll be going over computer internals and a little review over what Elijah has covered over the last week. So, to give you guys a little intro to me, I do mainly DevOps stuff now for Rootkit. I have been specializing in AWS and handling our deployment of our educational platforms and any resources that we need, like our main website, for getting Rootkit in front of everybody out there. So this stream is a part of our 100 Days of Rootkit, where we are trying to educate everybody for free and show that you do not need college to become a successful developer. Come on over here to our website. You can get more information on how to follow us and support us. And then if you follow our links in the stream description, you can see how to donate to us without going through Twitch and having them take our big cut from it. We also have some wonderful merch over on our website. Off here. We'll be expanding this continuously. but we do ship international. All right. Without further ado, let's start getting into some of the courseware. So over the last week, you guys covered a lot of the nitty-gritty stuff about computers, a lot of the logic and the low-level data representation, how bits look, and how to do bitwise arithmetic, and then hex and octal, and all those really cool things, but they're low level. So the idea is, how do we translate that stuff into real world? Like, how do computers take those bits and do logic based on them? And that's what we're going to be getting into this week. Okay. So we briefly look over this. So we can see that we can represent data in many different ways, and you guys went over a lot of these. So we have decimal, binary, octal, and hex. And now these are all just data. And so the computer can interpret data in any number of ways. 8 bits can mean a coordinate on a 3D plane on where a character is located in a video game, or it can mean a temperature, or it can mean anything. So with that, we can take these data points and we can do logic off of them. And that logic flows all the way down to the hardware level. And so that's what we're going to be starting with, is how can we control computers at a physical level. Starting here, we'll step into our first book, which is titled Digital Logic. Begin looking at the different logic symbols that engineers use, because computers at a fundamental level is just electricity flowing through different types of gates. That is how we control things based off the logic of those gates. So we can represent these in the same way that electrical engineers represent them. So here we have a very simple gate, which is like a light switch, where if it's closed, the light is on. And then when you open it, the electricity cannot flow anymore, therefore the lights turn off. And so there's a very, very simple example of how we control everything, like our motherboards and how they function. And we can make this more complicated by having 2 switches in it, and if either one of them is off, it won't function, or an AND, where you have 2 in parallel, and if either one of them is closed, then the light would be on. And so we can keep building upon this and making it more and more complicated. Very, very simple switches to very complex with millions of gates in it. So if we scroll down here slightly, we can see a table which takes the same picture and it writes down its possible solutions. Welcome, Kwai. So with this table, we can list the different types of inputs from both sources, and then what the output would be if it was in serial and parallel for this picture. And this gives us all the possible combinations, and then we can do predictions based off that. Like if we want to do something if only both were on, or both were off, or one was on and only one was on. So we'll continue right along with this. And so then we get into this concept of logic gates, where we want to make electricity do what we want, because that's our fundamental element that we're working with. Even if you're programming or you're making hardware, you have to control and harness the electricity behind it. We often don't see computers anymore that use wind or water or other types of energy to do computations, because we've kind of evolved past that point. You can't really fit that big of a stream in your office to be playing games at 2 in the morning. So now, because these get so complicated, we have this black box concept where it scales very, very quickly, and you can't visualize what is going on inside that black box anymore, because there's a lot of different types of gates that are in there, and they could be multiple layers of gates. But in order to start understanding what's going on under there, we can start using that table again where we list out all the inputs and then the outputs. And that helps us map, a little bit of what's happening inside that black box. So if we pass 3 ons, we get an on out. But if we pass 2 ons and an off, we get an off. And if we pass on, off, on, we still get an off. And then on, off, we get an on again. So our challenge is to figure out how it's doing that and how we could reconstruct it if we wanted to on our own. So now we're going to start getting into the many different gates in there. And now we're only going to scratch the surface. We are not getting into electrical engineering. The intent is not to walk out of here and go build our own computers, as cool as that would be. We're just here to understand fundamentally what's happening in our computers and how we can better control it as a programmer. So our first type of gate is an AND gate. You guys have seen this already with Elijah, where it takes two signals and it ANDs them together. So only if they were both on does it return an on or a true. And so this is one of those fundamental building blocks that we will continue to build on. We then have our complementary AND gate, or actually let me back up. So the AND gate is represented as this like elongated D. This is important to remember because when we start plotting these and you're going to see multiple of them at the same time, as in like over here, do an and add that a while. And so memorizing to a certain degree what these look like is important so you can follow the flow mentally by yourself. So we can see here, if we connect to that the output is on, but if we turn one of these off, the output is off. So we can keep building on this periodically throughout the night so we have a visual representation of what we're learning. So our next type of gate is an OR gate. You guys have also learned about this, and it's a relatively simple one, once again, where if any of them are on, any trues get passed into it, it outputs a true. So if you pass two trues into it, it outputs a true. If you pass one true into it and then an off, it still passes a true, an on. And vice versa, off and then an on, it still passes an on. The only case that it's off is if you pass in two false values. So this is like an arrowhead representation. So we're starting to build up our bank now. We have an elongated D, and then we have an arrowhead. And then we have our NOT operator, which you guys have also learned about. This is a very simple one. This is the one that takes only one input. My favorite one. It's super easy to understand what's happening. So if we pass, whatever we pass in gets switched to its counterpart. So if we pass an on, it gets switched to an off. So pass in an off, it gets switched to an on. And then we have our NAND, so a neither and. This one's, very similar to an and, but with a not. So if we pass two values of on, they're both on, so you would think with an AND gate that it would return a true, but it's knotted, so it returns a false. Then the other three values do not have two ons, therefore they return a true because we're knotting them. And then we have our NOR gate, which is a neither or. Very similar to our NAND, where it's an OR gate, but knotted at the end. So if we pass either or in to being true, it returns false because it would return true, but then we knot it, therefore it's false. So I'll stop here for a little bit after covering these. You guys have any questions about these ones? Because after here, we start to get a little muddier on how they work. They get a little bit more complex. While you guys are thinking of questions, we'll come over here and play with them a little bit. Add a no. We'll start making some nice complex gobbledygook that represents how our motherboards look like. So I'll post this link in the chat because this is a really cool tool to help visualize logic. You can build out our quiz questions as we go. Yes, there we go. The link's in the chat. So if there's no questions, we'll move on from here. We got a few more to cover before we can start getting to the fun stuff. Okay, so now that we have these relatively simple ones that all kind of make sense, they're relatively easy, one or two inputs and a one step out or two step out output, where you either do the logic and then not it or just do the logic. We'll start stepping into some slightly weirder ones, which are the exclusive OR, which we've covered already. We have an exclusive AND. So the exclusive OR is, once again, like an OR statement. We're building off that concept, except it can only be either or. We want to be exclusive to that. So if two are true, it's not either or, even though they are both true, so it's false. If we pass one or the other in, it's true. And if both are false, then there's no signal whatsoever to be processed, so it's still false. And so with these sets of gates, these are the fundamental building blocks of how we can make more complex logic and do stuff like our AI aimbot, or do stuff like cryptocurrency trading bots, or build websites based off logic that do, if the password's correct and all that kind of stuff. Is all built off things like this. And back in the really early times of computers, instead of programming virtual bits, they programmed physical bits by moving them in these huge computers the size of warehouses, which I just think is fascinating. So here we're starting to show some of these more complex circuits where we take an and then an or an and, a not, and we have an or here, and we pass both of those into an and gate. So we can take this and we can rebuild it in our logic gate simulator and help us build out that output. We have two inputs. Output back, or turn them both off to start. And we have our AND gate on the top, our OR gate on the bottom. They both get passed in one of these nodes. Then we have a NOT on the top. The AND gate gets passed into. Have an AND to bring both signals together and pass it to the output. Sorry, the screen's getting a little small here. Back up. Straight up just a little. And then here we can start building out that table now, where we are trying to figure out what our inputs are and what they equate to as outputs. So you can see here they gave us a little bit of starter, whereas if we pass in two trues, we're going to get out a false. We can go check that. So we'll pass in two trues, and we do indeed get a false. And then what we'll do is we'll start by turning off one. We can see that one on and one off gives us an on. And two offs, like that. So then with that information, we can take that and build out our table. So we know that if 1 is on and 1 is off, we get a true, and vice versa, true, and 2 offs, we get a 0. And we can traverse this by just looking at the diagram as well, by showing that if we have 2 on, what we have going on here is they're both going into the and both of them are on, but then we not that. So we have two trues that come in and a true that comes out, then we pass that to a not. So we have a false that goes here. Then we say either or here get passed in. We'll take either one. So we have 2 trues going in, either or is true, so we have a true coming out, and we pass that to the and. Now we have a false and a true, which does not pass and. We have a 0 coming out. We turn that off. We have a yes and a no, a true and a false getting passed in. So this is a false, is passed to not, which is a true, so the top is a true. We say either or, so one of these is a true, therefore we get a true coming out of here, gets past the and, so we have a true and a true, so we get a true on the output. This is a reflexive one, so it works if we swap them. Same logic. So yeah, Kwai, so this was, our Learn site was an early attempt at us getting into the education sphere, because we really want to revolutionize education, and the fact that we think the current education system is kind of boring and misses the mark with training developers or any trade skill to a proficient level for the workforce. Because we were getting out of college ourselves and witnessing our friends and other people around us and colleagues getting out of college and lacking the real world skills to be able to excel at their job, whether it be the ability to explain what their project is to their other colleagues or to their higher ups, or if it was just the ability to get out there and learn on their own and Google, because that's a big skill that we have as programmers, is our ability to go out and research what we're doing. Almost nothing that we do is like super secret. You can break it down to pieces that you can go and Google, even if it's like some secret government project. So after this example, we make it a little bit more complicated. But instead of just having 2 inputs, because that's kind of simple, we now have 3 inputs. And we have a 3-gate system that's relatively simple, but we can see that our table has to grow to accommodate for the 3 inputs. If we have 4 for 2 inputs, we have to double that, because each piece after that adds a whole nother layer of possibilities. So we go build this up quick in our handy dandy interactive tool. We'll add an output, or an input, I mean. Put that right here. Turn them all off to start out with. Our junk that we got in there now. So we'll start with our AND gate that we have right here at the top. Have a simple NOT with 1 input coming from R. So place that down here. This one goes directly into that one. That's a very simple relationship there. And then we pass all of it and right before the output. Place that right there. Fire these up. They are in the diagram right here. And then we'll wire the second layer up to this AND that just collects all of it and passes it to the output. And now we can start our testing. So once again, we have a little bit of starter here, a little something to give us a shove. We can see that 1, 1, and 1, so all of them on, will result in it being off. Then we can start exploring. So we'll do on, off. And we see that it's on, so we'd mark that here. And we just keep going down the way, testing each of these solutions. And even without this, we could also just follow it by using our finger. The handy dandy old methodology works. So we turn these 2 on. We pass this to an AND gate, so true and true, we get a true out. we'll make this one a true. This one's an off, so it gets passed here to this not, so it flips it to a true, and it passes it here. So we have true and true, which is true, which is why our output is lit up. Now if we flip this to the next one, the third row, we have an on, off, on. So we pass this to the and, the on, and the off. We have on and off, therefore they're not both on, so it is off. Pass that to this top here, and we have an on, which gets flipped to an off. Pass the off on, so we have off and off. None of them are, they're not both on, therefore the output is off. I really like digital logic because you can follow through the entire process with your finger. There's no, big algorithms or, messy math that happens. Any question on this so far? Yeah, Koi. And the other issue with that is when instruction is just given in a sense like how we have on our Learn site, like if we just give that to a person, there is so much effort needed on the learner's behalf to absorb that knowledge. You have to read it. You then have to do further research to make sure you understand it. You have to do the exercises to reinforce the learning. And then you have to go out and apply it to something. Because unless something's relevant to us, we don't commit it to memory. And so just doing, 4-hour lectures in college and where I just preach to you, and then you go back and you take a bunch of notes, you try your best, you take your notes and you memorize it for the test. As soon as that test hits, you're dropping all that information unless it builds upon it in some way. And so it's just not extremely constructive or inclusive to learning what you want to learn and supporting the job that you want to support when you get a job. So our intentions in the future are to try and break apart these really complex topics. That way you can cherry pick what you need for your job or your desire to do. Like if you want to make a game, we want to break down all of the subcomponents for how to make a game so you can learn it how you want to learn it, at the rate you want to learn it, and the way that you want to learn it. That way you'll want to learn. Everybody should want to learn because we want to get better at what we're doing or what we want to do. All right, so this next page will show us our answers. So we can check some of these just to make sure that we did the second one right. We'll check. So if we pass on and off, see that we get an on. It's good. Then we'll skip down to the bottom. We'll do an off and an on and check that it is off. So off. Still have it off. So it's looking like we got it right. So we're gonna keep on powering through this stuff. Take a break after this lesson. The digital circuits and Boolean expressions. So now that we're understanding the physical representation of these gates, we now need to start representing them back into what you guys learned last week, which is how we represented on paper in logic. So we can build out these complex tables and understand how they flow and follow them better through programming logic. So what this means is that we have to take these symbols and equate them back to how we just were doing, where we say this is an and. So we can do a P, then a V, this weird caret symbol as for the and symbol, and Q. And for here we do P or Q. Here we do not P and Q because it's building upon this earlier thing where we have P and Q, and then we not the whole thing. So here's that P and Q from this previous gate, and then we just wrap it with the and from this gate. Then we have our P or Q. We pass that on. Now we have not P and Q and P or Q. So that is our end expression that we are trying to represent. So we'll build this quick so we can talk through it just one more time. We have two inputs, so we get rid of one, up a little bit. our and. So it's that top one, and then we'll do our or. Pass. Have our not at the top. In here. Screen that just to make it a little prettier. Take that not, we'll pass it into the top of the and there. Okay, so now for this first and, we'll get out old MS Paint and start drawing a little bit. So for this one, we're gonna do a P and a Q. It's pretty. There we go, just goes right off the screen. That's our first expression, first gate. We'll pass that to the not. So then we'll scroll down here with our not symbol, our wrapped P and Q. Beautiful handwriting, by the way. And then we'll do our OR gate over here, P or Q. Down here. Or wrap that. Well, now these are our two complete expressions. We have this not right here as this expression, and we have our or as this bottom one. Now we need to and both of these. So now we have our completed equation for what this output is. This is the entirety of it. So now that we have that complete thing, we can start solving for this. And we don't care what's in the black box because we have our full equation here. We have another representation here. And we'll check that we did this right. We'll see that we have our P and Q. Then we have our P or Q. Then we not the first expression. Then we and them together. And this representation I do like a lot because it uses parentheses very willingly to show each expression, as we can do here where we wrap this to show that this here is a full expression. But I do think it's a little overkill with the simplistic ones. And so now here we can just start playing around where we just pass in our tables again. So we can pass in a 1 for P and a 0 for Q. Pass in a 1. And then we'll carry the symbols down. We have our and. We have our or. And this whole expression. So now we converted this to the pretty zero thing. Sure, there's zeros, not O's or any other weird shapes. So now we've equated this into energy. We brought this back into our sphere of speaking in absolutes. Now we have an on, an off, and an on or an off. So we can do our and first. So we have a 1 and a 0. And we know that that outputs from our previous pages here. Back. Yeah, so we have our and. So we pass in a 1 and a 0. So a 1 and a 0. And we see that that outputs a 0. Carry our 0 down. We'll bring that and symbol back. Then we'll solve the right side. So we have a 1 or a 0. So we can plug that into our table here. We have a 1 and a 0. So we output a 1. Fancy 1. There we go. So now we're left with a pretty simple expression here where we have a 1 and, or a 0 and a 1. I passed 3rd grade. I know my numbers. So we come back up to our table. We pass in our 0. We pass in our 1. And we're output with a 0. Although I did forget about our not from earlier. So I forgot to not this side. Back up a step. Have a not here. So we'll equate for that where we have our 1 and a 1. Because we gotta do the parentheses first. then a not. So I have a 1 and a 1, which we can plug into here, and that outputs a 1. And we can go forward a few pages. Check our answer. So we pass in a 1 and a 0. See that we got a 1 out. Or, wait, 1 to 0. So I must have messed up somewhere. Different one. Oh, yeah, this is a different one. Just an example. Okay. On. So here we're doing a reverse now, where we took our symbols and we equated it to our values of 1s and 0s. That way we can translate it to binary and all the other data types that we know. And they're giving us an input table. And now it's our job to construct it into the logic gates. We need to make the mechanisms that do the logic on the energy. So here we're stepping down where we see that if we pass in a 1 and a 1 on the first row, so P or Q or R, we get out a 1. If the third row, and so we can step through here and we can keep testing each of these expressions to see how they're true. And we can keep building these up. So the line's really important. And if we keep stepping through here where we keep testing this and seeing if we can OR them together, not them, and all of this to make it true for each one of these inputs, we can then start graphing it out. And so we're doing the exact reverse of what we just did. So we can take these inputs and start plotting them using our handy dandy interactive tool. So we have 3 inputs on this one, so we'll add another input. Yeah, you're definitely right. Calculus, like, so when you get into machine learning and deep learning and any AI, well, I should say, a while ago, you had to be very heavy into the math side of things. But now that AI and machine learning has really started to mature, a lot of those nitty-gritty concepts and the logic and all of the math behind the scenes has been really abstracted away from us, which is an awesome perk of modern day programming. We get to use libraries and packages and software suites that have luckily taken a lot of that math and the theory behind stuff like that away from us, which saves us a lot of time and effort. If you just want to use something like an alert box on Windows, if you just want alert box to pop up on your application, you don't need to know how to write visualization tools for Windows because they've already done that for you. You just have to call the alert box. You don't have to understand the underlying how it connects with the drivers and speaks with the kernel and everything and asks for permission and then it displays. We just ask for it. And somebody else way smarter than me has done that for us. Start building out here. So we'll do our not. Those are 3 hands. Things get a little messy here. And they all get past it. Doesn't look like 3 here. That's fine. What we could do is just put 2 ORs together. Because that would be the same as having an OR with 3 inputs. It's not as pretty. Start wiring this up. R1. Oh, I forgot. ANDs only the 3 input one. So for ANDs, they do matter because you have to AND all of the expressions together. But for OR, because it's not exclusive, if any of them are true, it'll be true. So you can just daisy chain as many ORs together as you need. over 3 ands, so P, Q, and R all go into the top. And then we have this guy here where P, Q, and R go in here, but the Q is knotted. And we can do that because we have here is a P, Q, and R. First one, so second one. Go. P, Q, and R, and we knot this to get the true. Not which R, which is the third one. And then for on, off, we have on, off, get our one. We'll construct this piece right here so we can get an on, off, and get a true out. So we need on just to go right in. Then we need our two offs to get knotted. They become trues, and we pass that to an and. Because for an and to be true, they all have to be true and true and true. And then we can just pass all three of these to our ORs. Oh. So hook them up. Pass that right to our output. Now we can start testing to make sure we got it right. Kind of messy. We see that if we have 3 ons, we get an on at the end. We'll test it with on, off. So we'll turn our third. And we get an off. So we're good so far. We're doing pretty good. Do an on, off, on. Off. We still get an on. Okay, we're 3 for 3. On, off, and we're good. So we'll do the inverse where we have an off, on. Then we get an off, on, and so on. So we can use this in both ways. We can come from the programming brain, where we're using our ones and zeros, and we can translate it to physical logic, or we can take those physical logics and convert them to our programming brain, where we then want to build off of it. Or we can then build off of it in a programming sense using digital logic versus physical logic. And so now I just want to draw a quick parallel to what is physical logic and what is digital logic. So physical being anything that we can touch or manipulate. And digital is a concept where we are making something out of nothing, out of electricity. And so here we see that this gentleman here, Steve Mould, he made a water-based computer where he wants to do basic addition for numbers. And so using binary, he's able to construct numbers and add them up. So this is all addition that he's doing here.
This would be a substantial increase in computing power.
All right, here we go.
Okay, bam, we've had our and. Because that still could have gone wrong. Like, I know we're saying it's a trivial calculation, but that split had to work. And now we just need 2 slow leaks.
Which is what we've got. It's 0, 1, 1, 1, 0, which is 8 plus 4 plus 2, which is 14. What were we adding together again?
9 plus 5.
Is 14, yay!
In my
So here we can see that using a physical construct that does not do any switching. There's no moving pieces here besides the water, which is the input, which we could equate to electricity. We could replace this water with electricity if we switch, the gates around to not be empty containers, but to be logic gates on a motherboard or a circuit board. And so he just takes these and they're anding and oring them together and knotting them, so that way they overflow into the next basins. And if they're empty, they're 0, and if they're full, they're 1s. So I think there's a really cool representation of kind of what's happening at a really tiny scale on our motherboards we're passing data through. And we can do this with a thing called breadboards. Try looking up. Yeah, let's look at that. So there's a So things like these are super interesting because this allows us to pass input and output, or inputs and then take outputs out of it. And so then you can do different types of gates here by connecting pieces to this breadboard. And this is super nifty for like just learning and stuff like that, or even trying to build your own technology, because you can put in a pin and take out a pin and just keep playing with it. And you can have this set up so there's an LED at the end. So when you flip a switch, the LED comes on, or multiple. You can do arithmetic with this as well, just like he did with the water. So if we put those same gates here in that order, we could do a 3-number or 2-number addition, or 2 sets of 2 numbers. So 14 and a 0, 9 in binary. And so this is a blown up scale of PCBs. They have all these really, really tiny, like microscopic nanometer gates on them. And this is just a way blown up thing where we can more easily conceive this. Because I don't know about you guys, but like if I can't see it, it just doesn't make sense to me. So here we just explore this a little bit more. I'm not going to bore you guys by going over too many, but you can see that now we're incorporating other things where we start doing more knots or ands to it, or then we can build in XORs to make it work, because passing 2 ands to an OR, you could just do an XOR instead, because it would be the inverse of that. So you can further simplify these diagrams, just like we do in algebra when you were simplifying a expression there. You can take that and simplify these diagrams so they're easier to follow and they have less steps. So that's what we're doing here. So that completes our first book. And then we already watched our video. And so with that, we're going to take a 5-minute break. If you have any questions, now's your time to ask. Let me start the break now. All right, we're back. So I just want to answer Elijah's question in YouTube. I'm sorry, apparently YouTube comments are not coming through on my side, so I have to pull it up over here on my other computer. And we see Elijah asks, so is this how I can make a computer from scratch? Yes. So all a computer is a utility tool for doing logic. So these breadboards that we can make are very simple computers. We have ancient computers which went just based off gravity or just the sunlight, and they use them for navigation. Those are still computers, even though they're extremely archaic and aren't really what we consider computers. They still did logic based on inputs and gave predetermined outputs. So with these, you can make relatively simple computers. You're not going to be making a graphics card equivalent on a breadboard. Those are a little bit more optimized now. But computers come in all different shapes and sizes. If we look up other computers like a Raspberry Pi, these things are really small and they don't really look like a computer that we know. Like they're not gaming computers. There's no onboard graphics cards. There's no liquid cooling or even there's any cooling. These things are just air cooled and they just have some very simple outputs. They have 16 pin and then they have two USB 3s, two USB 2.0s, and Ethernet. And then they have some micro USBs here on the side and a C. And so these are really tiny computers. They have really small optimized ARM processors. So these are good for doing lightweight tasks. But once again, you're not going out here, you're not playing too much complex games. Like you probably play Doom on it and you play some simple games, maybe get Minecraft running, be god awful, some of the older versions of Minecraft. But you can still program these, and we can make like simple games like Snake on them, or do other complex tasks like you can use these to host email servers or websites. So these are still all different forms of computers of varying degrees of horsepower and hardware behind the scenes. So just before we get into our first check on learning, let's go back and talk about 100 Days of Rootkit just a little bit more. I know we're harping on it, but it's what we're here for. So why are we doing this whole thing? Why are we taking the time of our day to do these streams for 100 days in a row? It seems a little bit extreme to hold ourselves to that. But one, it forces us to come here and educate you guys, and you guys are loving it, so we're going to keep doing it. But our goal is to educate people so they can better live their lives. It's you guys. You guys are taking the time out of your day to come and watch us and learn. And we're here to help you guys learn. We want to make it better. We're trying to spread awareness of our nonprofit, Rootkit, and our mission to educate the youth, and well, not even just the youth, but anybody who wants to get into any trade. Right now, we're essentially focused on programming because that's what our strong suit is. But the more people we bring on, the more skills we have under our belt. And so today, I'm here in front of you guys, but tomorrow you guys can be in front of a different audience, teaching whatever interests you, what you go out and you seek to learn on your own. And then we're also trying to raise money for our operations so we continue to grow. Right now, we are solely funded, and we've just been doing this as a passion project. And just recently, we started taking our passion project and scaling it. We want to bring it to the whole world because when we originally started, we were just in Maryland, and now we're online. And we found that there's a lot of people international that have the exact same problems as we do here in the U.S. Education kind of sucks the way it is. So we want to grow this to everybody. We want to help as many people as we can for generations to come. So now we can talk about, a little bit darker side of it. How do we donate? How do you guys help us here? So there's different ways of donating. One is your time. If you do help us through our mission by, let's say, release something on our GitHub, which we can pull up, or helping us give a class, or coming and teaching us something really cool, because maybe we, aren't doing what we need to be doing perfectly. Maybe our Discord could be better, or our GitHub could be better, or any number of things could be better. You guys know these things. We're spread out, we don't, you guys are experts of your things. You can come and teach us. Everybody has something to teach everybody. But if you contribute through something like on our GitHub or Discord or doing public outreach, you get to champion role in our Discord, which gives you pretty much the same tiers as being a Patreon subscriber at, I think, is a byte level. So you get in on our private stuff. You get to have a voice. You get to champion role, so people look to you for guidance. which is an awesome responsibility to have. That's how I first started here. And you also get some benefits like some merch when we do our cool merch drops in our events. Like we try and go to conferences every once in a while. We do merch drops for that. So the other way is financially. So you can come here and you can donate directly to us via PayPal, which just comes directly to us. There's no middleman. And then we also have our charity stream set up through Streamlabs. So you can come here and you can help us get that bar going at the top of our screen, where you can see the progress and everybody else gets to see it, which is super awesome. We like to discourage going through Twitch because they take their nice cut of it. So these are the best ways right now. Then we also have merch on our website. If you want to support us that way, get something cool out of it. And then we also have our giveaways that we are doing on 100 Days of Rootkit as well. They can come here and every day subscribe or come here for the giveaways and do the certain things that it asks of you. And the more entries you get, the more likely you are to get your drawing. And I believe it's merch that we're giving away right now and maybe rolls, which is super awesome. So with that, we'll keep chugging along. Okay, so circuits everywhere, all the horror. So now we're getting a little complex. We have layer 1, layer 2, layer 3, and layer 4. So once again, we're starting to get gross here, but nothing here isn't something that we haven't seen already. We've been through this. And so now we can go through and we can equate our symbols and start writing out what it is. So I pulled up this cool image from earlier, which just has all these different symbols for engineering. We basically use just the first row here. We're not doing anything too funky. None of these complex ones or these more involved ones. So we can take this, half our screen, back to our quiz. And we can start breaking this down. We have our and here. We pass a 1 and a 1 in. We know a 1's going to come on the outside. We have this weird D symbol with a circle on the end. Then we come over here, we can equate to what that is. So we can see that this elongated D with the circle is a NAND gate, and we know how to deal with that because we learned about it already. So we can do a neither and, 0, 1, and we can even come back to our previous page, back into our book. I believe a second. Then we'll look right here. So we got this symbol, we have this simple chart. We're passing a 0 and a 1. Come here, we pass a 0 and a 1. We see that it's neither and. The only one that's false would be the and because we take the and if that's true, we not it. Because that's what the neither and is. He's not whatever the product is. So we see here that we have a 1 coming out. We have a 1 and a 1. Then we have our neither or. We pass 0, 0. So I can come down here. We can look at our neither or. We can follow the fact that we have 0 and 0. So this would return a false if it was an or. Then we not that to be true. We have a 1, and a 1 going to layer 2. Solve the top first because that's how my brain works, top down. So we have an or, so we have a 1 and a 1 getting passed in the or. So we put a 1 right here. We have a 1 and a 1 coming to our and. So we have a 1 here. We not that 1. We have an or, a 1 and a 0. Then we have this weird elliptical 1 here. That was the last one that we talked about. This exclusive or. This was the weirdest one that we've covered so far today. It's an or statement, but only one side can be true at a time. Both sides can't be true, unlike the or. We have a 1, exclusive or a 0. We pass in a 1 and a 0, and we get a 1. Check our answer. Oh, that's right. This one is a one where we had to submit picture. So we can't do an input here and get a nice pretty feedback, but it wanted us to solve a circuit, which we did, and we could show our work with that, but we got a 1 on the output. Then moving on, we have our next check on learning. Let's go to that. Okay, so then here, we're just doing the exact same thing, but without our engineering symbols, we're moving back into those discrete structures that Elijah taught you guys previously last week, which is what we just equated that to verbally. And so here we can do the same thing. Take our MS Paint, clear this. All pretty again. Go. So we do our order of operations. So we'll do a 0 and 0 or 1. Solve for this inside these parentheses here, and we just work our way from left to right. There's no voodoo magic that happens. Our order of operations are just the knots, our parentheses, and then our internal, anything else. We do 0 and 0. You know, we're going to get a 0 out of because it would have to be both true to get a 1 out of that. We have our 0 or 1. We'll move that down. And we know that out of that we get a 1 because at least one of these is true. Then we could solve at the left side because we have an OR on that. So we'll clear this whole thing. Just remember that we got a 1. Down. So we'll come down here, give our 1 arrow. And we have another set of parentheses. We have a 1 exclusive OR, a 0. And now I don't remember my discrete structures very well, so let's go look up a chart of those. It's pretty good. I'll just get back at you guys with a good resource finding these. But what we can do back here, and we can go into our previous book here and find it discrete structure. So now we have to remember where we have it in here. Really on set. Here we go. Here's where we have all our symbols that you guys covered last week. We have our and, our or, our exclusive or. We have our not. We have our if then. We have our if and only if. Yeah, this problem broke out for 8 pages. second. Okay, then with this one I had a brain fart, so I'll have to get back to you guys on that. For now, we'll just move on so we keep trucking along. So, hey Matthew, $1, but it won't allow me description. It just redirects me to the Streamlabs page with the stream. And you are doing that through the Streamlabs charity. Give that a shot if that's what that's doing. Seems to be letting me through. Link in the description. Seems to be letting me through. Link in the description. Seems to be. That's on YouTube that you're trying to do that through? I'll keep working on that on the side, Matthew. I'll try and figure that out for you while we're going on. Where were we at? Now we're getting down to computer memory and architecture. Start this book. So our computer's memory works as that logical medium where we take the physical hardware and we start passing in data to it and start storing it and manipulating it in different ways. So we have this manifestation nowadays as the CPU, so we have pictures here representing that. And we're just going to read a quick blurb about it. The current computer architecture is derived from John von Neumann's 1945 draft report of the Electronic Discrete Variable Automatic Computer, or the EDVAC. So von Neumann was a German scientist, I believe German scientist who was working a lot on the rocket programs. He was a brilliant man who came up with a lot of concepts and was very ahead of his time with stuff like computers and sending rockets to different planets, stuff like that. So his design architecture describes a stored program concept, allowing instructions and data to be stored in memory rather than being manually entered each time the program is run. We had this concept of taking that physical where some person actually sits there and they put the switch in and it controls exactly how it flows, to maybe making it software based. So you can control that in real time and program it virtually or digitally rather than having those big physical machines. And this would allow for optimizations and scaling. So It allows for a single memory and input-output, so an instruction fetch and a data operation cannot occur at the same time. This is known as the von Neumann bottleneck. The Harvard architecture, also a stored programming concept, solves this bottleneck by having separate memory and input and output for data read, data write, and instruction read, which allows for the writing of data to memory while the next instruction is being read. So von Neumann's concept kind of works like a straw. You only put one thing through it at a time because they only had one in and one out. If we just scale that up and just make multiple straws for each different instruction that you want to do, like a read, a write, and then just a write to memory, you can have more parallelism, allowing for more instructions to be done every second. So you see how people quickly start optimizing and iterating on the software-based programming versus like the big physical programming, which we do still use in terms of like train tracks. If you have a train where it has a split in the road and you want to pull the switch to make it go left or push it to go right, that's a logic gate. That's what old computers used to do. Here we have RAM, where random access memory is used to put information on it, hold it there for a short period of time. If you power off your computer, you lose all the data on your RAM because your RAM just needs to be constantly powered to hold that memory. And this is where we could do things like do complex algorithms where you have two sides of it. If the computer wants to solve the first one on the left side, it can put that product then in RAM and wait and go solve the second one and then pull it back out of RAM and then put them together, manipulate things. When you load into a video game, a lot of game engines will load a lot of assets into your RAM because your RAM is very, very quick at discharging back out to your computer. So if you preload some of your like big intensive assets, like graphics, like the new weapon skins and everything like that, you preload all that into RAM, it's much easier for you to call upon it repeatedly. Then we have an input-output mechanism here, where we have some old VDIs and DVIs and a display port here. These are just examples of input-output devices. Your keyboard, your mouse, your monitor. When you go to like the store and you use their point-of-sale system, they have the credit card machine hooked up to it. That's just a computer with a credit card machine. That's an input and output device. It outputs to the screen to tell you that you remove your card. It takes input from your card. So by providing this information and this mechanism for storing and processing information, we now have complex software-based computing. It no longer requires you to go out. What are instructions? That's a good question, Elijah. So instructions are any instruction. That's exactly what it says it is. So like an instruction would be to turn left. And we can explore that later on by playing some little games where we do simple instructions. So it would be like programming in, a monster in a video game. You want to chase a player. Well, you have to tell it how to do that. So you have to tell it go straight, go straight, go straight, go straight, turn right, go straight, go straight, go straight, turn left. And you have to give it each one of those steps to achieve its goal. So that's how we do it for computers as well. So if we want to turn on, it has to follow a whole process of turning on. And it's in serial. So you do one step, and then step 2, and then step 3, and then step 4. Each one of those is an instruction. Okay. So memory is a device that is used to store information for immediate use in a computer or related computer hardware device. Once a program is ran on a computer, it is given a chunk of memory that is split into several unique sections. This is a huge breakthrough. So you have this big brain that is the computer now. It has a bunch of memory, just like we do, to store things up there. Well, we don't just store everything because you can't. There's just not enough space in our head. So what our computers do is they take a chunk of the RAM and they say, okay, we're going to allocate this to each program. And each program gets to only use their memory. They're not supposed to be able to access anybody else's memory because that'd be a risk. We don't want mind readers running around. If you have one program which is doing like banking and transferring your credit card, then you have another one which is like a shady game, running potentially a Bitcoin miner on your computer. You don't want that to have access to your other program's memory where your credit card is being passed. So how do we subdivide this memory that's allocated to us? So we have our stack, we have our heap. Our stack is on top and it grows down, and our heap is on the bottom and it grows up. So we have these static variables. The variable lifetime or extent is the entire run of the program. Then we have our non-static variables. This variable will lose its value automatically, even if it is ever out of scope. So this static variable is something like your name. It runs for the entire length of your life. You know your name, you remember it, you're not going to forget it. You keep it going. Remember your age. Those are long-term memories that you're going to keep with you. But these non-static variables are your short-term memory. So when you're in a room and you're like, oh, I have to go switch the laundry, and then you walk out of your door and you immediately forget, it's because you switched scopes. You switch the scope from your bedroom into the hallway. And so that variable that you stored that memory in to go switch the laundry is gone now. It got deleted. So it's really important to understand for computers as well, because if you store something in a non-static variable or a temporary variable, and then you switch scopes and it's gone, but you try to use it, either the program is going to crash or it's going to pull some data out of nowhere. It's going to look at that same memory that I allocated earlier, it's going to pull whatever data is in there, which is just random stuff at that point, and it's going to try and give it to you how you want it. And so that could be used for exploits, or it could crash your program, crash your computer, who knows what it's going to do. It's really important to remember what scope you're in and how you want to manipulate that. And the reason we do this, again, is because we have limited memory. If we stored everything permanently and we never forgot anything, we'd very, very quickly run out of space to remember anything. You'd never be able to learn anything else because you'd go and you try to learn something else, there's no room, so you just don't. You'd have long-term memory loss, like just nothing would be there. So we use these short-term variables to remember things that maybe aren't that important. Maybe it's like a number that we're counting, how many times people go through the door. Then once we get that number, that final number, that's when we commit it to long-term memory. We no longer care about those short-term memory numbers. So this allows us to cut down on our program sizes. So now, we said that our memory looks like this. This is notionally how it stores our memory. So we have our stack, like I said, and it grows down, and our heap that grows up. If these ever meet, we have an issue. They'll start overriding each other. Your short-term memory will start overriding your long-term memory, and that also breaks things. We don't want that. So what computers have done is they've gotten really smart, our operating systems. Every time you get close to this, they just keep on growing until they can't grow anymore. So if you run out of RAM completely, either the program crashes or the computer has to crash. So the operating system plays it pretty safe and normally just crashes the computer, or the program, I mean, not the computer. So our stack memory used by non-static local variables explicit declared in a program. A CPU can access and manipulate these variables very quickly. So it keeps these close because it knows they're going to be changing a lot. Like for counting people that are coming through a door, every time somebody comes through that door, we have to increment that number. And we have our free space, which is just in the middle. It's just memory set aside for stack, heap, and other uses. So when the computer initially gives you a chunk of memory, I'll get to your question in a second, Elijah. It's another good question. So the stack is used by non-static, so our short-term memory up here. The variable, so a stack loses its value automatically when you change scopes. A heap is your long-term memory. So what the computer does when you initially ask, so you start up Notepad, it initially gives you an amount of memory that it calculates that it thinks that you'll need. And it normally has some cool things where Windows now does analytics based off your last time using it. And so it'll give you a little bit on the stack, a little bit on the heap, and it'll keep the rest of it that it thinks you may need in the near future in your free space, so you don't have to come back and ask for it. That's pretty smart about this, because every time you have to go back and you have to ask for more memory, the computer has to figure out how to get you more memory. That's expensive, so it doesn't want to do that. This free space is built in for you to use when you need it. So our heap is dynamically allocated memory that is uninitialized. So there's crap data in here when we get it. We don't know what's in there because the computer doesn't want to take the time to clear it for us. So we have to remember to clear this when we're using it, and most high-level programming languages do that for us now. But it's another important thing to remember, because if you allocate some memory and you immediately start pulling data from this, who knows what you're going to get. It may be usable, it may not, it may crash your program. So it's best to initialize everything and clear it out when you need it. This requires the application to request space for writing and reading to. Access to the heap is slower than access to the stack. That's why we want to use our stack for like repeat variables, and then our heap for storing long term. So Elijah asked, what is scope? So a scope is, like I said, kind of like our room. You can define each room in your house as a scope. So like right now I'm currently in my office scope. I store all my office memories here in my office, all my short-term ones that I want to learn. So if I'm learning how to draw, I'll store each step of how to draw in my short-term memory here in this room. And I'll try and remember the big picture of how I drew that picture, and I'll store that to my heap, my long-term memory. That way when I walk out of the office, I still have, my big picture. I remember kind of how to draw, but I don't remember every detail, because every detail was left in my office scope. That helps you out there. And then we have some other special ones that are down here. So we have the BSS, which holds global and static variables that are uninitialized or initialized to 0. They exist through the entire lifetime of the program. Once again, these are good, but us as programmers, we don't manipulate these directly. That's why it has a dot in front of it. These are for the OS and our hardware to edit. They're protected from us for a reason. So it protects us and it protects other people from accessing it. And then we have our data section, which holds global and static variables initialized to a non-zero value. So in a program, if we say that I want my age and I want it to initialize to 18, we'll start at 18 regardless of who that person is, and then we'll ask them. And so if they provide an answer, we'll update that initial one. So for me, I'm 25, so we change it to 25. But if I said I don't want to answer, then it would just assume that I'm 18 because that 18 is already in there. It would carry that on. These also exist throughout the life of the program. Just be careful when you're making these global variables because they don't go away. So if you start up Notepad and Notepad creates a bunch of global variables, for as long as you have Notepad open, that memory is being used, which we just don't want. We don't want to be memory hogs because you don't want to open Notepad and then not be able to open Chrome. And Chrome's already a memory hog. And then we have our text section, which stores the compiled code of the currently running program. So this is important because if we didn't store it here, we'd be storing on our hard drive, where it is already. So it's a little bit of duplication, a little bit of waste. But the speed that we get from our RAM versus a hard drive, you get to reach out every time your program wants to do something to the hard drive, it slowed down significantly. Instead of getting 120 FPS on Rust, you'd be getting 10 to 15 FPS, or even worse, because it's that much slower. So if you take that piece of code that we know we're going to run, so the code that we have to run now, and maybe some code that we have to run in the future, and maybe some other code that we may or may not run, and we store that in memory as well, it allows us to use it very, very quickly. And then you just throw it away when you're done. So just to reiterate, the stack and the heap start at opposite ends of the free memory and they grow towards each other. If a stack or a heap buffer overflow, that typically occurs when they meet. So we've heard this statement before, buffer overflow. I'm sure you've seen it either in shows, movies, or just other media like games and stuff like that, or news, where if these meet, so if our stack starts getting into our heap and we can start setting variables here permanently, we can manipulate how the program runs and maybe change something. Like if it only allows us in if our age is 18, and we create a bunch of other variables to the point where we get to our age variable and we change that to over 18 because we're under 18, now we can get to a part of the program we weren't supposed to be able to. Okay, so why are all these layers important? So these are in the weeds concepts, right? Like none of us are going out here and saying, for any programming level above Fortran or C, you don't go out and say that I want something on the stack or I want something on the heap. So it's semi-irrelevant because you're not manipulating this directly. But it's really, really important to understand when things go wrong, why they're going wrong. Or why when you open up an unoptimized Unity game, why it is taking up 12 gigs of RAM for a very simplistic game where you're running around on a flat ground. It's because they're storing a bunch of stuff probably in their heaps where they are just loading assets and storing it. They're loading NPCs and they're storing it. They're loading all the graphics, AIs, and everything, and they're just storing it all in there. And it just keeps growing. But let's say we create a program, maybe a banking app. A bank hires us to make a banking app. But every time a customer makes 10 transactions, the program crashes. It's important to understand how this memory is accessed for us to go in and debug and fix those issues, but also for our design. Because if we're designing with this in mind, we'll design more robust programs that are quicker, smaller, and better for our consumers. Why are these layers important and types on how to memorize all this? Tips. Okay. Is memory layout even important? Okay, so I kind of covered that. So the tips that I was always taught is like it's not too important which one's which per se, but the fact that we have these protected and that you can't be accessing these directly. But the big thing is that one is static, so long term, and one is non-static, so short term. And then honestly, to memorize which one is which, the stack being non-static, just S and S. Like I don't have any great tips for it other than this memorization, unfortunately. But I do like this visualization. For some reason, seeing it in play makes it click in my head. And another thing that we could do is we can also just draw it out, which I've definitely done in the past when trying to understand this concept. So if we have our stack, our heap, and we know that our stack is used by non-static local variables, so we can start adding in here a counter. Then we'll say we are long-term, we'll store like our name. We always want to know the person's name. That's counting the people in a door. We'll say age. I know how to write. Cool. And if we just keep writing different variables over here, and we keep expanding our stack because they're in our local space, and if this overrides our heap at all, you'll see that we start to clobber what was there already. So now we just overrode age with whatever variable we wanted here. So we could do, I don't know, like, I don't know, favorite animal. Beautiful handwriting, but yeah, so you see here that we just overrode that memory. So that memory that was there in the heap is no longer accessible to us. It no longer exists. We wrote over it. And so seeing like a visualization like this about how the computer is writing to that is, I think, good to see it in action. And then theoretically what our computer would do, and does all the time, absolutely all the time, is when we get to like a certain percentage, so it says like, oh, you're 50% full, it just grows this section more. So it just takes the heap and reallocates it down further so we get more memory. I like that. Heap is like a heap of leaves in the fall. It won't always be there. All right. We're going to take a 5-minute break here because that was quite a lot to digest, and I'd like to let you guys do some of your own research or try and commit it to memory and how you want to. And do you have any questions? Oh, we have one over here, Orange Hue. Are there online tools that examine executables? There definitely are. But I don't know about online tools being the best for this, because if you have an application, let's say calculator, it takes up 100 megabytes of RAM, and you pull it into your web browser now has to interpret that data, so it would have to be 100 plus megabytes. So generally these are tools that are offline. Like Kali Linux has a bunch built in for doing reverse engineering, or if it's written in .NET, so anything by Microsoft, you could use like .NET Peek, which allows you to look at the underlying code and step through it and understand exactly what's happening. There's other ones like OllyDebug or Valgrind that do very similar stuff, where it allows you to see the memory in action. And Valgrind's even cooler, or there's some other debuggers out there that will even let you like step by each instruction and see what it does to the memory. So it says like, oh, take age, oh, store age here, and you can follow that memory. And look up engineering. There's some other cool ones. Here's a cool one, Ghidra. This is made by the American NSA, where its whole purpose is to have a bunch of tools built in here where you take an application, you pass it in, and it reverse engineers it. It lets you see the variable names, lets you see the memory, lets you see what it's doing, what files it's writing to, and a bunch of really cool stuff. So if reverse engineering is something that you're really interested in, I highly recommend Ghidra. And it has a really big community, tutorials, and everything. All right. At this, we'll resume at 8:35 Eastern Standard Time. Alright, so we're gonna get started on our final phase for tonight. We're going for about 25 more minutes. So I just want to come back to this question I made earlier here, and I was struggling to remember what the down arrow meant. So I went and I looked up a page of multiple symbols. I found this really helpful Wikipedia page. It has all of the logic symbols just listed out in order of commonality. Really awesome. We see our downward arrow here. It's also known as a Pierce arrow, and it's a sign of the NOR operator. So the neither or on here. Okay. So I don't see any further questions on this page. Keep trucking along. Okay. So we have memory organization vulnerabilities. So software vulnerabilities are weaknesses allowing an attacker to violate the security of the software system. Underlying hardware level security design can induce software vulnerabilities like integer, buffer, and stack overflows. Programmers must be aware of these vulnerabilities created by the organization of main memory and data type specifications. Let's get back to the point where if an attacker knows that your stack is huge and it keeps overriding that to get into the heap, they can take advantage of that, and that's known as buffer overflow. They can get data that they shouldn't have access to, or put data that they want there, such as a different memory or different code they want to be run. And there's many different flavors of buffer overflows and stack overflows and all that. So, getting into buffer overflow, a variable that holds more than one value, such as an array, a vector, a string, basically any list of things. So if you have a big long grocery list, you just keep storing item 1, item 2, item 3 in there. That's our buffer. A buffer overflow occurs when too many values are written to our buffer. So if you make your grocery list or laundry list just way too long, and you go right off the page, then it causes data to be written outside the buffer allocated memory space. So if you're writing this on your desk and you fill up your whole page and you just keep on writing, you're now just writing on your desk. And that's out of the scope that you want to be writing on. So the overflow may cause abnormal behavior, example of terminating unexpectedly or corrupting data. So that's another big thing. So, if we're storing license plate numbers of people who ran red lights and somebody does a buffer overflow attack on us and just starts wiping out all the data there, we could potentially be losing a lot of money depending on if we're like the company that runs that software or if we're the government hoping to get our ticket money. In more serious cases, a buffer overflow becomes a software vulnerability. The C programming language defines a string as an array in a list of characters. So we don't really need too much more into this, but the C is very manual programming language. It's low level. So if you go out and you say that you want an array, so a shopping list of 8 items, exactly 8 items, it'll never be more than 8 items, and then you start writing to the 9th item, the 10th item, because C will let you, you can try and access that. And now on a modern day computer and a modern day compiler when it runs, it's going to handle it pretty cleanly where it's probably just going to be your program crashing. And most of the time they won't let you read from memory that you don't own, especially on Windows and stuff like that. So this has been mitigated to a certain point, but your program still is going to crash. Or some other weird stuff where like if you're in the middle of writing to a file and you have a buffer overflow and then it might corrupt that file. So I'm sure you've seen that happen in video games before, heard of it happening in video games, where the video game it crashes and then it has an error that spits out. Then when you try and load the game back up, your save file's corrupted. So it's important to know about these things and to avoid them. And there's some famous exploits that have happened if you're less interested in the programming side, more interested in the exploitation side of this house. A while back, 2012-ish, I don't remember exactly when Heartbleed was, but Heartbleed was an example of a buffer overflow attack. So it was a very serious overflow bug, was called Heartbleed. It affected every single web server in the world. Heartbleed was a security bug found in the OpenSSL library. So OpenSSL is used to encrypt our web traffic. When we go to a website, we have that pretty lock icon. These are encrypted using SSL. So every website using it. So pretty terrifying when you get a vulnerability in that. So this library is what is used to encrypt HTTPS web traffic. The bug allowed hackers to overflow a buffer, allowing them to view other people's web traffic on the server. This attack was against web servers, so like our Learn site. And so they'd hijack our server's memory to be able to see anybody's data accessing that website. And so it's any of their web traffic. Let's assume that it's a website like our merch store where we're taking people's credit cards for merchandise and we're taking your address and your name and all that information. The attackers would have been able to get access to that. So, and steal users' credentials and a whole host of stuff. So really bad exploits can happen. They can get a lot of information from stuff like this. The good thing is Microsoft spends a lot of time, a lot of money, and they have a lot of people that go out and hunt for these things and fix them before they get out to the public. But when things like this do get out to the public, they're very quick to roll an update out the next day or within 2 days to hopefully fix it. And it's not just Microsoft, there's a lot of companies out there. So that was a buffer overflow referring to the heap. So now we have a stack overflow. So the goal of a stack overflow exploit is to overwrite the function return address of a function pointer. So we'll strip that of all that, the nerd speak. So what it's doing is it's trying to overwrite an instruction with its own instruction. So if I tell you to go to the store and pick up eggs and milk, they yell louder than me and they tell you to go pick up candy because that's what they want you to bring home. So it's like a kid yelling candy. And so you go to the store and you pick up candy because that's what the last instruction was. Because you already forgot mine. They yelled louder than me. And so this is also terrifying because it allows an attacker to be running arbitrary instructions. I didn't intend for you to go get candy. I only had enough money for milk and eggs. So now I can't get my milk and eggs or the process. Or you could put in instructions to, steal information or to do things a program's not supposed to do, like access a database or something like that. So when excess data is entered into one or more local variables, this is how this is done. So because that stack is at non-static local variables to that scope, so the quick turnover, you'd have to create a bunch of quick turnover variables. There's a lot of those short-lived variables to overwrite the heap. Okay, this is getting pretty in the weeds here, so we'll keep this at a high level. So let's talk about the different ways that these really smart guys that made and designed CPUs and processors, they went out and they built them in a couple different ways. And each normally have their advantages and disadvantages for why you would do one or the other or why you would use it. So like our phones will use a different processor type than our computers. And that's because phones are more specified for doing simpler tasks like answering phones, sending texts, like answering phone calls and sending texts and stuff like that, where our computers are better at complex things like physics calculations or encoding music or rendering videos and just a whole host of problems. So we have our CISC architecture, which stands for Complex Instruction Set Computer. This is a type of CPU architecture, has usable instructions, can process more instructions in one cycle, and is more complex than a RISC counterpart. So this complexity generally allows for better performance to be achieved on a CISC-based processor than a RISC-based processor. Most of today's servers, desktops, laptops, they're all going to use CISC-based processors. So that's x86 and x86, 64, 64. An example of a CISC, or these are all examples of CISC architectures. Like when you're installing Windows and ask, or like you download Minecraft and says you want the 64-bit version or the 32-bit version. That's what this is referring to. So all of the CPU companies like Intel and AMD currently make CISC-based processors. That's because these processors, they are more complex and they require a lot more energy. So that's why you have these big power supplies in our computers like 650, 750, and even up to 1,000 watt power supplies now, because modern processors take 100 to 170 watts versus your phone, which is taking double digits, like 10, 15 watts. They're really optimized for energy because you want your phone to last throughout the entire day. Processor doesn't, or your computer at home doesn't care about lasting all day on a battery. They can just draw more energy from the wall. So they want more horsepower out of it. So we have our RISC processors, which is a computer architecture using only one low-level operation per instruction. So basically you say to do one thing, so I tell you to store. I want you to go to the store, and I can only tell you to get one thing. I want you to go get bread. You come back. I tell you I want eggs. So you go back to the store, you get the eggs. You come back to me with the eggs. I want butter. You go back. So it's one-to-one. So much simpler, much more streamlined. And this is used in a majority of smartphones, tablets, cars, anything, your toaster, your refrigerator. these are running RISC processors because they're super efficient energy-wise. Recently, Apple came out with their new line of laptops utilizing their M1 chip, which is RISC. So yeah, Apple finally got on board a few years ago when they came out with the M1 chip with their MacBooks. So with AMD and Intel. So x86 and ARM processors address memory in bytes. The order in which data is stored in memory is known as Indian, pronounced as like an Indian, like a Native American Indian, or byte order. So there are two types of Indianness. We have a Big Indian and Little Indian. In Big Indian, data is stored most significant byte first. This is similar to how people read. So this is left to right in English. A lot of these standards were based off English speakers. So Big Indian reads from left to right, which is not what computers do. Computers do Little Indian, where data is stored in the least significant byte first. And the reason for this is there's some optimizations with doing Little Indian, which is why like sometimes if you're looking at how your computer is doing networking, you'll see it'll say like com, then the website name, and then like the subdomain of the website, and it has it like in reverse order for how you would type it in as a human into the web browser. It just allows them to access the relevant information faster. So I have a question. What brand CPUs are one versus the other? So most RISC-based processors are made by really specialized companies that are now blowing up. And I mean, because phones blew up when processors were first made, smartphones were not at all in the vocabulary for these people. Nobody expected them to have to be storing these processing chips on things that we put in our pocket. And so that like the early processors weren't designed for that. So then we had to get some other big names to come in. So like Intel, looks like they even open source RISC processors. There's definitely some other companies. I just don't remember the name off the top of my head. Yeah, I know Qualcomm is one of the major manufacturers in the world for making smartphone processors. I don't remember if Qualcomm is the one that Apple uses. Oh, because Apple uses Qualcomm. Oh, Taiwan Semiconductor. Okay, that's right. So Apple uses TSMC, which is Taiwan Semiconductor Manufacturing Company, and then a lot of the others, Samsung and stuff like that, will use Qualcomm. I believe TSMC signed an exclusive contract with Apple. I believe this will happen early on. I have to get back with you on more of this. It's been a while, so I've looked into exactly who makes what. But definitely a lot of our like modern day processors that we're seeking, like for building these big gaming rigs that we want, we all want the Intel i9-13900K, the latest and best beast processors made by Intel. That's a CISC. And we also have our AMDs, like our Threadrippers and all those big, huge CPUs that AMD is making now to one up Intel and make better gaming rigs. But also both companies are making these CISC processors that are specialized in making like video editing processors or machine learning, stuff like that. So a lot of the big names like Intel and AMD are very focused on CISC because that's where a lot of the profit is. And then Samsung and Apple and other phone manufacturers are more interested in RISC. And so they're going for manufacturers like Qualcomm. All right. That finishes up our second book for the day. And then we're going to save our check on knowledge and we're going to do some quizzes first thing in the stream tomorrow to make sure that we're retaining some of the information. So at this time, are there any questions on the content that we covered today? Anything that we should go over second time? Then I also just want to show you guys, if you hop in our Discord as a supporter or a Patreon, we also have our companion guides that we post after every stream on here. And it'll be a quick summarization of what we covered for the day. We'll give some test questions on there just to do some check on knowledge there. And also all the resources that we use. I'll link all the websites that we went through, and any relevant information or questions that popped up will be in there as well. All right. If there's no further questions, I'm going to go ahead and end the stream here. I'll see you guys tomorrow at 7 p.m. Eastern Standard Time.